Hey everyone, Roland this side. I hope you all are doing well. So let's say the problem of the day.
Okay, so today's problem is 2812. We have to find the safest path in the grid. So basically we are given a 2D matrix of grid called of size n cross n. Basically we are given an square matrix of size n cross n where R and C represents I mean where R and C represents a cell containing thief if this where row or column it's row and column. Okay, so basically grid RC equal to 1, that means the cell is containing a thief, and if it's 0 it is an empty cell. Okay, so for example we have matrix something like this. So if any so rest of the cells will 0, and if any cells contains 1, so basically if this cells contains a thief. Okay, so what we have to do, basically we are initially positioned at 0 0, so we are initially positioned at 0 0. Okay, so that's our start, and we have to reach we have to reach to the end of the matrix. Okay, so basically we have to reach to n minus 1 n minus 1. Okay, so this is the finish. Okay, we have to reach here. So what we should take care of, so basically we have to take care of the safeness factor. Okay, the safest the safeness factor of a path of grid is defined as the minimum manhunt distance from any cell in the path of any thief of grid. Okay, so first let's understand what is manhunt distance. Okay, so it basically the sum of horizontal and vertical distance between any two cells. Okay, so for example if we have something here like 2 3 4, something here like its index is something comma 1 comma, okay, its index like 0 comma 1. Okay, and its value is for 1 2 3 4 4 comma 2. Okay, so what is the manhunt distance between these two cells? Okay, so it's basically a vertical distance what is which is 1 2 3 4, and a horizontal distance which is 1 2. Okay, so it's basically gonna equal to 6. You can also do it by simpling. This is 1. Okay, so 5 4 plus 1 is 5. So we can also do this by simply doing difference between x coordinate, that is 4 minus 0, plus difference between y coordinate, that is 2 minus 1, and that's whole. Again we can take mod of these two, and this sum gonna give us 4 minus 0, that is 4 plus 1. Okay, so it's overall gonna become 5. So that is manhunt distance between any two cells. Okay, so the safeness factor of a path of a grid is defined as the minimum manhunt distance from any cell in the path to any thief in the grid. Okay, so basically what are the safeness factor to a path? Okay, so basically we have to start from 0 to n. Okay, so basically we have to start from 0 and reach to n minus 1. Okay, so we have to choose a path to reach there. Okay, so what was the we have to choose the safest path. Okay, where the safeness factor is most, so we have to choose a path where we have the maximum safeness factor. So we have to choose a path with maximum safeness factor. Okay, safeness factor. So what is the safeness factor of a path? Okay, so for example, for that we have to understand this safeness factor of a cell. Okay, so first of all we are going to understand safeness factor. Just ignore this spelling. Safeness factor of a cell. Okay, so what is the safeness factor of a cell? So safeness factor of a cell is basically, it's the minimum manhunt distance between any all of the thieves. So it goes something like we have one, we have thieves here. Okay, so what is the, we have two thieves in this grid. Okay, so what is the safe safe factor of this cell? So what is the manhunt distance from this grid? Okay, so if we see that this grid manhunt distance is 1 2 3 4 5. Okay, and from this grid it's 1, so the manhunt distance is 5 and 1, and for this it's 1 2 3 4 4 and 1. For this it's 1 2 3 1 2 3. Okay, it's gonna become 2 here because this is 2, and this is gonna become 3 comma 3, and similarly it's 1 2, so 2 1 2 3 4, so 4 2 comma 4, and somewhere it goes like yes, it's 4 comma, I mean 1 comma 1 2 3 4 5 1 comma 5, and here it's also gonna 1 comma 5 because 1 2 3 4 5. Okay, 1 2 3 4 5, and it's 1. And here it's something like 2 comma 4, it's 3 comma 3, it's here 1 2, so it's going to become 2, and it's 1 2 3 4, so 4 comma 2, and it's 5 comma 1. And for this, if you see 1 2, so this is 2, and this is 1 2 3 4, so 4 comma 2. For this, it's 1 2 3, and it's 1 2 3. And for this also, it's going to become 3 for both. Okay, 1 2 3 1 2 3, and 1 2 for this, and this 1 2 3 4. Okay, so we get something like, say, we can have multiple values here. If here we are getting only two values in each cell because we have only two thieves in our grid. Okay, so we have to say what is the safeness factor of this cell. Okay, so this is the minimum and 100. So what is the minimum between 1 and 5? So it's 1, I mean 1 and 5, it's okay, let me create a fresh new cell. Okay, so it's something like this. And what is the safeness factor of here? So it looks, and for this you can see the what is the safeness factor of this cell. So distance from this cell to this, it's 0, and for this 1 2 3 4 5 6, it's 6. Okay, and for this 2, from this thief, okay, I can mark this as a green cell because it is a thief cell. Okay, here we contain thieves. For this, the distance between this to this gonna become 6, and from, I mean, and from this, I mean from its own, it's the distance is Manhattan distance is 0, and from there it's 6. Okay, so something like this. So we got the Manhattan distance from all two thieves, both thieves. Okay, all of the thieves. Basically, we have two thieves here. Now we have to, I mean, get the, we have to calculate. We have to get the minimum. So this is the Manhattan distance. Manhattan distance. Okay, but now we have to get the minimum across all, I mean all tools, all of the thieves. Here we have only two thieves, so here minimum is 0, minimum is 1, minimum is 2, here 3. It goes something like this: 2 1, we got 3 here and 2 here. Okay, so we got minimum. So this is the safeness factor of cell. Okay, safeness factor of cell, so we can say call it a safeness. We can just gonna call it safe array. Okay, safe grid. Okay, so it basically represents the safeness factor of our, I mean, grid. Okay, I mean all cells. So what is our objective basically? So basically we have to travel from this to this. Okay, so we can choose a various path. Okay, so now for example I'm gonna choose a path. Okay, so let's choose a path. Okay, let's travel from here. Okay, so what is the, I mean, safeness factor of this path? Okay, so safeness factor of safeness factor of path. Okay, so the path in blue. So this is, I mean, so this basically the maximum number. Okay, so it's the safeness factor is the minimum. Okay, so is it minimum? Yeah, the return the maximum safeness factor of the, for the safeness factor of a path of a grid is a minimum and distance. The safeness factor of a path of grid is defined as a minimum and distance from any two cells. Okay, so we have to the minimum and distance. So we have to get the minimum of this path. So the minimum of this path is 1, and if we took another path, for example, we took a path like this. So what is the minimum of green? Okay, safeness factor of path. We can also call this minimum. So what is the minimum in green path? Okay, so it's 2. If we can, okay, now it's 0 in blue basically. If we see carefully, it's 0 in blue, and in, I mean, pink, if you see it goes, if we take a path like this, Okay, so what is the minimum of this pink color safeness factor of pink path? So it's 1. Okay, so what we have to return? We have to return the maximum safeness part of that grid. Okay, safeness factor of that grid. So we have written the maximum safeness factor of all paths among, I mean, the grid. Okay, so among the grid we got this is maximum. So 2 is maximum. So what is the safeness factor of path? It is the minimum safe value, minimum value of the safe cell across the whole path. Okay, so safeness factor of path, if we going to write the definition of safeness factor of a path, so it goes something like safeness factor of a path equal to minimum, I mean value of minimum value across all safe cells. Hold on, minimum value of safe cells across path, across whole path. Okay, so safeness factor of a path is a minimum value of safe cell across the whole path. Okay, so okay, now we see the approach how we are going to solve. So what, I mean, now we have to think logically how we are going to code this. Okay, so first of all, I mean, the first thing we are going to do is you have to first of all create this. Okay, this safe grid. Okay, so how we are going to create this safe grid? So first part is to create the safe grid. So how we are going to create this safe grid? So for example, we have, I mean, let's make another one here. So we have this one where we know thieves are here and the rest are empty cells. So what we are going to do is we are simply going to do a simple. So okay, so first and most brute force approach is to go to each cell and calculate the Manhattan distance from all the thieves and then return the minimum. For example, here we need, I mean, if we got two thieves here, so I mean, individually we have to calculate whole. Okay, so we have to do the BFS from, I mean, every cell we have to do the BFS from each of cell. Okay, each of cells. So we have to do BFS from each of cells. Okay, so BFS to, I mean, whatever the time complexity of BFS and to m n square. Okay, so basically it's n times n. So n times n. So I think that's one. I mean, that's going to become too much. Okay, so what we are going to do is simply instead of visiting every cell, we are going to visit every thieves. Okay, I mean every thief cell, and we're gonna mark something like this. Okay, so how we are going to do this is first, I mean, let's consider we visited this cell. Okay, visited this cell. So now what we are going to do is, so we visited this. Now what we are going to do is we are going to, I mean, do the BFS over this thief cell. Okay, I mean we are going to look for left, we are going to look for up, right, top, and gonna increase the, I mean, from its 0. I mean, what is the value of this? Okay, so it's basically 0. What is the minimum and distance from the thief? So it's always gonna be 0 because it is the closest to himself. Okay, so what is the next? So next is just one in one, I mean, increment of this. Okay, so what is the minimum and distance from this? So we're gonna mark it as 1, and now we are going to do BFS from each of these. Okay, so for this we're gonna left, down, top, I mean it's left, top, right, bottom. Okay, so for this we are going to increment it like 2 2, so it's gonna become 2 2, and again increase is like 3. Okay, so it's not 2, it's basically down. This one is 2, so we got a 3 3 3 here. And for similarly we are going to do this simultaneously. Okay, so basically we are going to be simultaneously from both. Okay, so we are going to use a queue to do the BFS, and what we are going to do, we are going to push both thieves along, I mean in once. Okay, so let me show you how we are going to do this. So for example, this is our queue data structure. So this is our queue data structure. So what we are going to do is, let me write the indices. So it's something like 0, 1, 2, 3, 0, 1, 2, 3. So we are going to push the first thieves. So for example, we are going to push 0, 3 and 3, I mean 3, 0, 3, 0. So this is the first round of VFS. So from 0 to 3, we are going to look top, bottom, right. Okay. So from 0, 3, we are going to look left and down and top and bottom. So there is no top and right. Okay. So we are going to only left and bottom. Okay. So left, we are going to increase it by 1 and push it into our queue. So it's 0, 2. Increase it by 1, push it in our queue. That is 1, 1, 3. Yeah, 1, 3. And there is no, right and top. Okay, so that's it. So we got 1, 1 here. Okay, and if for the thieves we are going to replace it by 0. Okay, while pushing it we are going to replace thieves by 0. Now we got this. So now we are going to do for this. Okay, so we done this. Now do for 3, 0. For 3, 0, we are going to look top and right because it has no left and bottom. So for top we are going to push it 1, so it's 2, 0. And for right we are going to push it, increase it by, from left, previous, do a plus plus, from previous do a plus plus. So we are going to increase it by 1 and gonna push it's 3, 1, 3, 1. Okay, so this is the second window you can call up. And now for the second layer. So well, if you see, basically we are doing a layer wise. This is the first layer, second layer, first layer, second layer. Okay, so this is the first layer, this is the second layer. Now this is gonna be the third layer. Okay, so like that. So now the next gonna become, so we are going to for 0, 2. So it's 0, 2. So we are going to left and down. It's gonna become 2. So that's 0, 1. It's gonna become 2 also. That's 1, 2. Now this left one is already visited and there is no right. Top one is also visited, so we are going to look for the bottom one. So we can do this is 2. It's 2, 3. And we got 0, 2 and 1, 3 for 2, 0. So 2, 0, we are going to insert the 1, 0. Do it 1 and it's a 2, 1. Do it, increase it by from its own value. So do it 2, 1 and another one, this one, gonna do left and up. So right and up. So up is already visited, so we are going to do the right the 2. Okay, so what's this? This is 3, 2, 3, 2. And simply if we add it over this, so we are going to increase it by 1. Also with this by this by this or any else, depends on implement of our BFS. So that's how we are going to create our array. Okay, create our this safe matrix. Okay, so after creating the safe matrix, so we have to simply check it. So okay, so first we created the safe matrix, and second of all we have to check it. So okay, so the first way of checking this is like, let's consider we have a function called check. Okay, so what is basically does is it take input, it take in input our grid, the safe grid. It's going to take input our safe grid and the safe value. Okay, safe value. So for example, we have to check for every safe value. Is 1 is safe? We can find a path with safe value 1. Safe factor 1. It's safeness factor. Okay, so are we going to find a safe path with safeness factor 1? Yes, we can find a path with safeness factor 1 here. Okay, so can we find a path with safeness factor 2? Can we find a path with safeness factor 3? So we can simply do 1, 2, 3. 1, 0, 1, 2, 3 until we broke. Okay, so we can do this linearly, or the second thing we can do is we can start from 0 and took int max, or we can do it by binary search, or instead of int max we can what we can simply do is, instead of doing int max, we can do also one thing. We can simply take 2 into grid size, 2 times grid size, because at a max it can go till that. Okay, it can't gonna limit. Okay, if we are not going to get more safe than this. Okay, so we can to the gift set, and we are going to do the binary search. Okay, so first of all, what is the mid of 2? So it's gonna be somewhere around green search. So n, so is n is the safeness factor of this path? If yes, so what we are doing, n is already safe, so we have to increase the safeness factor. Okay, so we are going to move low, it's low, it's high, so we are going to move low dash to here. Okay, and high remains here. So now it's something like, I mean, for example, we got something like 6. Okay, so is 6 is a safeness factor, and here it says 8. Okay, so it's is 6 is also safe. So if it's 6 not safe, we are going to move high, one less than. Okay, so it h dash, and by doing this simple binary search, we are going to, I mean, call this safe function, check function. Okay, so we are going to call the check function inside a binary search. Inside a binary search, we are going to, I mean, call the check function, and at last we are going to return the high, because that's the maximum we can get, the maximum safe we can get. Okay, we are going to, we have low, high. Okay, so at that we are going to return high. And now the last thing we are left with is how we are going to check is, I mean, how this check function gonna work, how we are going to check. Okay, so we can check pretty straightforward. If you see, I think we are already done this. So now we have to left with check function. Okay, so now let's see. We got our safe grid. In our case, it's somewhere like 3 3 3 3 2 2 2. Uh, don't get hallucinated with the pattern. It's because we have the symmetrical thief, so it's occurs. It's made up like this. So what next? What we are going to write the check function? Okay, so first of all, we are going to do the BFS to also to check this, is this vector is safe for us. Okay, so basically what we are going to do is, simply we have the safe factor going to start from 0 0, and if, I mean, we have to keep moving. Okay, so our safe factor is, for example, we have to check for 2. Okay, is 2 really possible? I mean, okay, so we can't, I mean, we can't go more low than 2. Okay, so we have to keep our safe factor. I mean, if we want our path to have safe factor 2, so we can't go to any cells where safe factor of the cell is less than 2. Okay, so we have to keep our safe factors greater than equal to 2. Okay, so we simply do the BFS on 3, and if at any moment we got less than, I mean, a cell is less than our safe factor, so we are going to continue. Okay, so because we cannot visit, we are not going to visit in our BFS, and if any point we reach the n-1 cell, we are simply going to return true. Okay, inside our BFS. Okay, and if after completing the whole BFS we are not going to, I mean, we haven't returned true, so at last we have to return false. Okay, let me show you how it's gonna work. So for 3, I mean, now we are considering the safe factor 2. Okay, so we can only visit greater than or equal to 2. Okay, so is it 2? We have to do BFS. So BFS is gonna look for left, right, top, bottom. Okay, so we got the next cell as 2 and 2. Okay, so is 2, I mean, greater than equal to 2? Yes, so we are going to visit here, we are going to visit here. Okay, now we are going to push these 2 and q. Okay, so for example, we push 3, then we are going to push 2 and 2, then 2 on a call. So can we visit 1? Okay, no, we can't visit 1 because 1 is less than 2. Okay, so we are not going to visit 1. We can visit, I mean, 2 here. We can visit from 2, we can visit 3 here. So we can not visit 1. Okay, now can from 3 we are going to put this 2 and gonna push this 3 1 here. Okay, from 3 we can visit 2 2. From there we can visit this 2. We are going to push again this 2 here. Now from this 2 we can't visit 1. We can't, I mean, we can't visit 1, or this is already visited, so we are going to do this again, and 3, and again like this. Then we got 2 2. and 3. Okay, so this if safe factor is 2, we got two paths. Okay, so basically we have to return is this safe or not. If 2 is safe, we are going to try for 3. So can we go for 3? So let's say it's 3 really possible. So we got 3, so we have to keep it greater than equal to 3. Okay, so we started from here. Now we can't go here because it's less than 3. We can't go here because it's less than 3. And if we can't go here, so we are going to we are going to continue over every cell, and our BFS search gonna break out. It's gonna I mean it's gonna exit, and at last we are going to return false. Okay, so for 3 and for 1, we are not going to check the low, but for example, if we are checking for 1, let's take this color. So if we are checking for 1, what we got. Okay, so can we go to 2? Yes. Can we go to 2? Yes. From 2, can we go to 3? Yes. Can we go to 1? Yes, because it's less than equal to 1. Okay. Can we from this 2, can we go to 1? Yes. Can we go to 3? Yes. From this one, can we go to 2? Yes. Can we go to 0? No, we can't go to 0. Okay, because 0 is less than 1. And again like this. And yeah, we can simply do the all PMCs because path really doesn't matter. What here matters here is the safeness factor of the path. Okay, so that's I think that's it, the whole code. On what we are remaining about the time complexity of this code, we are going to discuss this further after coding. Okay, so let's first code it. Okay, so first step is to create the safe grid. Second step is to I mean do the I mean binary search on safe grid, and it one after that return true. Okay. And for binary search, we have to write the check function, so that wanna become our search. So write the check function. So that's the whole code in 3 steps. Okay, so and one more thing I want to mention here is look what we didn't do binary search is starting from 1 in while creating the grid here. In while checking, we do binary search from started from 0 0, but while creating we inserted every thieves in one every thieves at once. Okay, then started our what we call this uh, BFS. Okay, BFS, sorry, binary search, it's BFS. Okay, so it is also called that multi-source BFS. Okay, we can also call this multi-source BFS, and the name doesn't matter unless until you unless you know the code. Okay, so basically we got the approach. Okay, so now let's code it starting from where our steps. So first let's create the safe grid. Yeah, and that worked actually. And if we really want to discuss about the time complexity and space complexity of the code, so uh, this two this gonna took n square n cross n. Okay, so this gonna took n square to visit the all, and the while we are traversing the we are going to visit every cell only once. Okay, so this also gonna take 1 cross n square. And for this, yeah, now this become, so first we got the check function. Okay, so check function gonna take the what is the check function gonna take. We are doing a simple VFS where we are visiting our each cell in worst case. So check function gonna take time complexity of check function is basically n square. Time complexity is n square. Okay. So time complexity of check function is n square. And if we see for this while loop, so and time complexity of while loop is somewhere log n. Okay, so it's n square times log n. Okay, so total time complexity gonna become n square times log n. So for this while loop, the BF, if we see the time complexity gonna become n square times log n square times log n, and we can take it log 2n. Okay, so this log in is of what we should binary search, and this n square is for BFS. Okay, we are doing BFS inside binary search, so this we end up by multiplying. In space complexity is simply an square. We are creating another what we call the safe grid to track all of it. So here's the time complexity and space complexity of our code, and I think yeah, that's it for today. I hope you like this video, so please make sure to subscribe to Tensor, okay, and feel free to ask any doubts if you have in comments. And till then, keep smiling and keep coding.